All right, so we're picking up from the last video where we designed an induction coil for our ZVS annealing system, and here's what we had settled with: 3.25 turns per layer on a 2-layer coil, and with our 3/16 copper tubing, this was expected to give us around a 0.8 inductance. So I started working on this and I realized I didn't actually have the correct fittings that I was going to need because I'd actually used all the ones that I had on different projects. So went to hardware stores went to a couple of them, and it's just really hard to find 3/16 copper tubing and the correct fittings. You can find some, but not the exact ones that I wanted. And so I'm going to make a change to this design just for practicality. And I'm going to try something because in the last video, I'd kind of poo-pooed on using 1/4-inch copper tubing because I just thought it was going to be too big. I thought that it was just going to be really hard to get tight bends with it. But I'm going to give it a shot. And the reason is that it's just so much easier to find 1/4-inch copper tubing and fittings. You can get basically everything you need from Home Depot or Lowe's or an Ace Hardware. Whereas if you're using 3/16 tubing, it's actually just pretty hard. You got to try to find this stuff on Amazon sometimes, and even then it can just be hard to find the fittings and everything you need. So I'm going to give this a shot, and let's see what happens if we change the specifications. So our conductor size, instead of being 3/16, we're going to need to change this to a 1/4-inch. So if we take 1/4-inch in metric, that's going to be 6.35 millimeters. Okay, so I've increased the pitch also to 7 millimeters just to account for the larger tubing. Is still going to have a gap, and so that just makes it kind of easy. It's going to give us like a 0.65 millimeter gap, and who knows what it'll actually end up as, but let's calculate. And so we've got a 0.75 microhenry coil. That's really not a big change from the like 0.78. Let's see what that does to the frequency. So it does change our frequency to about 124 kilohertz if we're using a 2.2 microfarad capacitor bank. If we turn this to the 3.3, if we change this to the 3.3, it's going to be 101. Now, again, just to point out where we were at a 0.7859. And so you can see it's just a few kilohertz. It's really not that big a difference between these two. All right, so again, you're just talking a little bit of shift, and that's not going to make any difference at all. So as far as the electrical properties, using 1/4-inch versus 3/16, really no difference hardly at all for our purposes. That is a total non-factor. One other change that I have to make is that I looked, and the best form that I can find is actually a 1/4-inch dowel rod that I've got. And it's 19 millimeters, so I need to recalculate. Now you can see, once I adjust for that, again, we aren't going to change the inductance really from the previous example. We don't have to redetermine anything here. The same exact coil design is going to work just fine. We end up with a 0.7969 microhenry inductance. And if we plop that in, you can see 120. Or if we go to my particular set of capacitors, which gives me a 3.3, 98 kilohertz. Again, I am totally happy with that. It's not going to amount to anything really as far as the differences in this design versus what I had talked about in the previous video. But it is going to allow me to try that 1/4-inch tubing, which again, all the fittings and the tubing itself is just way easier to come by. And so let's give this a shot. So I'm going to move outside, and we're going to show you how to wind this thing up. All right, so I've got my copper tubing here, and I'm going to measure out about 3 feet, which may seem like too much, but you do want to remember to leave yourself tails because you do have to attach this to your system, and you're going to need to put on fittings, and you can't wind it all the way tight, you got to have something to hold on to. So you do have a little bit of waste in this process, but trust me, you'd much rather cut off a few inches extra at the end than find out that you don't have enough and have to scrap the whole coil. So you don't want that. All right, so roughly about there. So you could use a hacksaw for this, but I actually, in the flaring kit that I've got, it came with this little pipe cutter. So that's what I'm going to use. It does leave a nice finished edge. So it is a little preferred to using a hacksaw, because a hacksaw you kind of have to do some deburring afterwards. Get this thing on. Okay, so this thing cut. And there it goes. And like I said, you get a pretty decent little edge on the end. Protector on the other end. Hey, you can see this end they gave was not quite as good, but that's okay. So the next part is get some pliers, and we're going to crimp this closed. You do want to make sure that that is all the way crimped shut. Get it really nice and packed in, because we need to fill this thing with kitchen salt. So we got a different pair of pliers to do this, because the other ones didn't give me quite the leverage and ease of use that I wanted. Okay, I ended up using the vise to finish this off, so we got a good crimped in there. And this is important because you cannot have this thing leak, because our next step, we just fill this tube up with regular old table salt. Right, so again, just regular table salt. I've made myself a little paper funnel. Put that down in there, and now you just need to get it good and full. Give it a little bit of a tap while you're filling, just to make sure it's good and packed in there. That's why you do want to make sure your tube's a little straight. Apologize for the noise. Neighbors have decided today's the day. All right, so after you tap it, it does settle some. So you do want your tubing to be pretty good and straight, so that you don't leave any kinks or anything for any of this to get bound up, because you do need it packed good and tight in there. Okay, so we've got it full of salt. It's good and packed in there. Tamped it on the ground to make sure it's tamped. So now we've got to crimp this end to make sure that everything is really packed in there tight. Once again, we want to put a bend in this. All right, so now that we've got our ends crimped closed, and I didn't get this one fantastic. I do have it kind of crimped, but it was starting to, this stuff being thicker than what I'm used to, it doesn't crimp as easy. But I do think that's going to be good enough so that it doesn't let any of that salt out. So the next thing is we are going to set up our core and get to winding. All right, so getting this thing started is definitely the hardest part. So, you want to make sure you got a good grip, and you want to make sure that this first bend is nice and tight up against your core. Give yourself all the leverage. That thing bends. Now, as you go along, if you're using insulation, you don't have to worry about anything, because these aren't going to be touching each other. Since I am not using insulation, I'm going to be using this to make sure I get separation as I wrap these coils. Because again, it is very important these things do not touch each other, or else they conduct, and that shorts your coil, and then you don't get the right inductance. you do want to make sure you do this before you put the second layer on. You're not going to be able to get to it at that point. And it's okay if your coil ends up a little longer than planned. Again, it doesn't have to be that precise. Okay, now the next step is to add the second layer. Now, first let me illustrate, this is why you can't just do 3 turns, because this is 3 turns. We go 1, 2, 3, and you can see that we end up going basically out the same direction. So this is why we've got to end up doing that half turn to come back. So at this point, I've now got to start bringing this wrapping back down. And again, keeping this stuff separate electrically is important. So I'm going to take some paper and I'm going to fold it in half a couple times. So I've got like 4 layers of paper. And then I'm going to put that underneath this so that as I wrap this, I have something of a barrier. And that will keep this coil from wrapping too tight on top of the other one and causing it to short. So I've got these separated out, so I've got good gaps. Dog making an appearance again on the coils. So now I've just got to fish this paper out, and it's, you know, you can tear it, you can soak it in water and get it out. It'll come out. That's not going to be a problem. So also, if you've got any final bending to do on your tails to get it to match up wherever you need to go, now is the time to do it. You don't want to do it after you cut these, because once the salt's out, then you can collapse your tubing again. Let me get the paper out of this, then we'll do some testing to see how we did, get some measurements and see, you know, how it tests on inductance. Well, he's just going to lay down and have a good time. Okay, so I've got this little LC tester. You know, I got this off Amazon. It's not the best. It kind of is a little funky to use. But it's the best I got, so let's go ahead and get this thing zeroed out. And let's test this coil. Got all the paper out of it. I still haven't emptied the salt, but that shouldn't matter for this test. So we're showing about 0.63 microhenries, which is, you know, not necessarily what we had planned on. But, you know, here's the thing. We actually, you know, my manufacturing was not also what we said it was going to be. So this is what's interesting, all right? So 0.63 microhenries, but let's actually measure this coil. All right, so some cheapo calipers. So the internal dimensions, spec'd at 19, yeah, that's not too bad. So that's fine. The internal dimension's fine, but if you test the height of this thing, it's showing like 32 to, depending on where you measure it from, 32 to 34 millimeters tall. If I measure the diameter, showing like 44 on the diameter. Okay, so if we look at kind of what was specified, also the difference here is close to 13. This coil is bigger in this dimension than I had planned on. Right, so it's a taller coil than I thought it was going to be, which means the spacing on this kind of axial pitch was more than I had planned. Now the radial is a little smaller, and that's because these tubes kind of nest a little bit. But, you know, that height actually does make quite a bit of difference. You know, if we rebuild this thing, we say, all right, well, the interior was like 19.1. And then I entered the axial pitch as 12. Now, originally we'd had it at like 7, right? And we said, oh, it's going to be, 0.79. But the reality is it ended up being quite a bit bigger. I left much larger gaps. So it's more like 12 millimeters. The pitch here you actually can't shrink because it'll give you an error saying, hey, these conductors are this big and they can't be that close, because it doesn't take into account nesting, right? These things have to be stacked. So, that's about as close as we can get it realistically. And if you calculate this, you actually see it is very accurate. This calculator is not the problem. My manufacturing was the problem. So the reason why my inductance was not as high as expected is because I didn't make the coil like I said I would, right? I ended up with a higher axial pitch. So, basically what that means is the inductance that I'm actually measuring, which is the more like 0.63 range, is surprisingly close to what happens if you actually specify the coil that you build rather than the one that I thought I was going to build. And so, it turns out the calculator works fantastic. I'm kind of surprised at how accurate that thing is. Who knows? The meter may be off. This is as accurate as I think you could possibly hope to get. A couple things to take away from this is, it might be good to over-specify the inductance of the coil because I think that the errors I made are probably pretty systematic. You are probably not going to be able to make something with as tight an axial pitch, with a 0.5 millimeter perfect spacing. You're probably going to overshoot it a little bit. So, you might want to plan for that. So let's see what this actually changes about the frequency that we should expect. All right, so if I plug in 0.63 microhenries here, you can see with a 3.3 microfarad capacitor bank, you should be looking at 110 kilohertz. Now, if you're going with a smaller capacitor bank with 2.2, it does kick that frequency up. So, it might be worth making a little bit bigger of a coil if you're using smaller capacitance. But I will also point out, this is fine. 135 kilohertz, there's nothing wrong with that at all. That's not going to be a problem. I would say even up to 150 or maybe even 200. I haven't done any testing, and based on the books that I've read on this, I don't think it's going to be that big a difference. Now, you don't want to go too high, but it's more of a problem. You want to be, up above 75. At lower frequencies, especially once you get down to like 20 kilohertz, it becomes audible, or it can be audible. And that lower frequency is more for iron and ferrous alloys. You want a little bit higher frequency for better coupling with brass and copper. So that's really what's driving this frequency range. The other part of the frequency range that you don't want to go too low is because you're basically wasting some power. In that higher frequencies have what they call lower skin depth. And so since we're doing thin brass, you don't need too much depth in the heating, and lower frequency is more for like forging, where you need to through heat something, get the heat really deep. At higher frequencies, you basically only heat the surface, but when you're dealing with very thin walls, that is full depth. And so that's the other part of the frequency. So it's really not that big a deal as long as you don't go so high that it's starting to give you skin effects in your brass. But I think we're definitely in a good range here. This is a fine coil. So for the next step, I'll show you how to get the salt out, and it's pretty easy. Okay, so now we got to get the salt out of this. So here's the trick. We're going to use a flare fitting on this to hook this up to this adapter. And so I got this off Amazon. You can probably find them at Home Depot and some other places. This goes on to a garden hose fitting. And so basically you can hook this thing up to a hose bib on the outside of your house, and then the water is going to dissolve and push the sand out of this coil. And I found that this works pretty well, very reliable. The salt definitely kept our coil from collapsing, right? We got good round cross sections, and it's gonna come out. The water is going to dissolve the salt. The pressure from the hose bib is gonna push all that out, and we're gonna be left with a nice clean coil. The other methods that people usually suggest for this are sand or ice. Fill the coil with water, or fill the tubing with water before you wind it. Freeze it so that whenever you wind the thing, it's got ice inside. I found that sand works great for keeping the coil from collapsing, but then you can't get it out. I have 2 or 3 coils filled with sand here on the table because I found no good way for getting the sand out of these really tight bends. It just packs in there. And, you know, I've heard some people say you can blow it out with compressed air. I don't have an air compressor, so that doesn't work. It's just nothing I could do to get it out. It just ended up stuck. The ice, while you can get it out very easy because it just melts and turns into water, didn't really keep the tubing from collapsing. It does okay, but what I found is, number one, it's kind of a hassle because you've got to fill the tube up underwater and then get it crimped off so that it doesn't leak, and that's kind of tough. That's one way if you want to do it with water, not ice. If you want to do it with ice, you can't crimp it first. You actually have to leave the ends open because the ice will burst the tubing if you let it freeze while it's crimped. But then once you start winding the thing with the ice, I found that the ice starts to melt and then you get some collapsed tubing. Because, you know, as you wrap this thing, some heat gets built up. It starts to melt that ice. The ice is less dense than the water, so you end up with some voids, and then you get some collapses. And it typically doesn't totally collapse. I'll try to show you on this one. You can see kind of right there how this, it kind of flattens. So yeah, you could still get a little water flow through there maybe, but it's just not the nice round cross section. With salt, you get a nice clean round coil. And as we're about to see, you can get that salt out pretty easy. So I'm going to go ahead and get this hooked up, get this thing flared, get the fittings on, then we'll watch it work. Right, so we got our fittings on. Let's get this thing hooked up. All right, so go. So there we went. I walked inside to get a pair of pliers to tighten that, and literally 10 seconds later, there you go. Well, she's cleared out for sure. I'm gonna turn this off so I can get this thing detached. All right, so there you go. Yeah, I mean, that took maybe a minute and a half, 2 minutes, and now it's completely flushed. The last time I did this with a smaller diameter tubing, the 3/16, it did take a little longer. I think with the 1/4 inch, it's just easier. The salt crystals are smaller relative to the internal diameter, and I think they're a little freer flowing through this. So it blew out really quick. But that's kind of all there is to it to making one of these things. You know, at this point, it's as easy as just trimming the other side or getting these things to whatever length. Now, again, I do recommend that you get them bent all into shape prior to opening them up and getting the salt out, because at this point, if you start to bend them, you're going to be much more likely to kink. But yeah, so that's how I make induction coils. At this point, you know, you probably want to, if you've got an air compressor, blow some air through it to dry it out. But since it's going to have water inside it anyway, it's really not that big a deal, or coolant or whatever you're using. But, you know, that's the way I do this. So best of luck if you're making these things. I hope that's a good process for you, and I hope it's all clear. Once again, if you got any questions or comments, just leave them down below, and I'll try to answer as best I can.